So this lecture today is going to build up pretty heavily upon some of the concepts that have been covered in the past couple of lectures. So just to review some of those briefly, a set sigma of well-formed formulas is going to be satisfiable if there exists some truth assignment that satisfies every proposition in sigma. So if there exists some v such that alpha under v is true for all alpha. And we say a set of well-formed formulas logically implies alpha, and we denote that as such if for every truth assignment that satisfies sigma, it also satisfies alpha. Yes?
On that line of v, you mean v half of alpha, right? There exists v such that you mean v half of alpha.
Yeah, so I'm just going to be dropping the hat just to keep things simple. So it should be understood that anytime we're feeding a well-formed formula, it's the v hat, and then if it's just a proposition, then it's without the hat. So logically implies means that for all v that satisfy sigma, then you know that it also satisfies alpha. Okay? So those are the basic definitions, and then we've extended some of these to include notions of maximal satisfiability as well as completeness. So completeness means, so again, sigma of well-formed formulas is complete if for any propositional formula alpha, it either is proven by sigma or its negation is proven by sigma. Okay? Yeah.
Sorry, can we turn on the lights? The phone is, I think it's
Sure, yeah. Thanks. Is that better? Okay. And then we say it's going to be maximally satisfiable if, again, for any alpha, whenever we have sigma not able to prove alpha, then we know that it's not going to be satisfiable. So as Shai was saying at the end of your last lecture, intuitively what this means is that I've kind of got a sigma that knows everything. If you take any well-formed formula alpha and you ask me about it, either I can't prove it, or sorry, either I can prove it, in which case I'm not in this case, or I can't prove it, and then it's not satisfiable. So either it contradicts something I already have, or I can already prove it. It's basically what this is saying. So these are a set of definitions that we're going to end up playing with a lot. These first two are most important for this lecture, but I just wanted to also recall at the end of last lecture, you proved the following theorem, that basically sigma is complete and satisfiable if and only if sigma is maximally satisfiable. And in order to prove that, we just basically juggled with these two definitions. But one kind of important fact that we'll use a couple times throughout today's lecture is kind of you can kind of think of it as a generalization of this theorem that applies for any sigma and any alpha. The fact basically establishes a relationship between what it means to be satisfiable and what it means to logically imply alpha. So the fact is that sigma logically implies alpha if and only if sigma together with its negation is not satisfiable. And to see that, you basically prove it in the same way that we proved it the theorem last class. You just look at each of the definitions and what it means for that to be true, and then show that that must be true, and then you can show the converse as well. And since this is if and only if, we can also negate both sides, right? So it's also going to be true that if you can't prove alpha, then this thing is satisfiable. So we'll leave that as an exercise. But we'll use that a couple times throughout today. Okay, so now what we'll do is introduce the following theorem. So this theorem is related in some ways to this, but it's a lot deeper and ends up having a lot of connections to some of the things you'll see on later in the course. So we'll spend most of today proving this theorem and another theorem that's deeply related to it. We'll call the theorem finite models. So what this theorem says is that for any sigma that implies any alpha, there exists some subset of sigma where, crucially, this subset is finite. And this finite subset also logically implies alpha. So in some ways, this is kind of surprising because what it's basically saying is that no matter what our sigma is, it could be infinitely large. If it proves some alpha, there's always going to be some smaller version that we can take to also prove alpha. So in some senses, this is kind of like good news for propositional systems because it means that we don't need all of our evidence in order to prove alpha. We can always find some smaller set. But again, this is, yes?
So is it always a proper subset, or can it just be sigma if sigma is finite?
So yes, if sigma is finite, then this is trivial because, yes, let's write this down just to be clear. So if sigma is finite, then this is trivial because sigma is a subset of itself, and clearly if sigma proves alpha, then, and we call this sigma naught, then that also proves alpha. So this really isn't interesting in the case where sigma is finite. It's really only interesting in the case where it's infinite. And so we're going to have to think about how to prove this. So does anyone have any ideas about a way that we could try to prove this? So, yes.
So is alpha finite? Because it's a well-formed formula, right?
Yes, so alpha is finite, but the set of propositions that it could have is infinite.
So then can we take only the elements of sigma naught that contain the propositional variables in alpha?
Yeah, so that's a good idea, and that was my first instinct as well. So let's try that out. So the idea is basically restrict sigma to the variables in alpha. But if we start trying to do this, we're going to run into some problems because our set of propositional variables is potentially infinite. So I can come up with the following counterexample. Say I let sigma be P0 or P1, P0 or P2, and basically keep repeating this for an infinite number of propositional variables, because sigma can be infinite, and we can also have infinitely many different propositional variables. So if that's our sigma, now suppose our alpha is P0. So if we were to restrict sigma to P0, it would still be infinite. So that's going to be a problem. So it's not going to be quite that easy. The main intuition is going to be even though both sigma and the set of propositional variables is potentially infinite, the truth table for alpha is finite because alpha is finite. So what we're going to do is look at the truth table for alpha. So what's this truth table going to look like? So we've got our propositional variables, and if we were to list all these out, we're going to get some set of truth and false values for alpha under all of these different truth assignments. And since alpha is finite, the number of entries in this table is going to be 2 to the n, where n is the number of propositional variables that occurs in alpha, and n is finite. So now, what are we going to do with this truth table? Well, the goal is to construct some sort of sigma naught that will logically prove alpha. And the main intuition is that we only need to worry about the entries where alpha is false. Because in order to logically prove alpha, you basically only need to be false, like, in order for sigma to logically prove alpha, you only need to worry about having sigma be not satisfiable when alpha is false. For the truth assignments where alpha is true, you don't care about sigma, right? Sigma can be anything. Does that make sense? So that's the intuition. The intuition is that we only need to worry about these false entries. But how are we going to use these false entries to construct sigma naught? So I'll leave this fact up because we're going to use it a couple times. So the main idea is we're going to let Vi be the ith truth assignment. for the false entries. Okay? So there's going to be at most 2 to the n such truth assignments. So in other words, vi of alpha is going to be false for all such I. Now what we're going to do is look at what happens with sigma under this same truth assignment. So consider sigma under the truth assignment vi. So what is going to happen? Well, we know that sigma logically proves alpha. So under this assignment, it cannot be the case that sigma is satisfied, right? Because if sigma were satisfied by this assignment, then it would not be the case that sigma logically proves alpha, right? So because sigma logically proves alpha, we know that sigma, well, let's leave that off for now. So because sigma logically proves alpha, we know that there exists some alpha I in sigma that is not satisfied by this assignment, right? Because if there weren't any members of sigma that weren't satisfied by the assignment, they'd all be true. So then sigma would be true. And then you'd have something true implying something false, which contradicts the definition of what it means for sigma to logically imply alpha. So just by working with these definitions, we've come to the conclusion that the truth assignment applied to some member of sigma is going to be false. Now, what are we going to do with this knowledge? Does anyone have any ideas? Yeah?
Add that to our construction of sigma naught.
Exactly. We're going to add all of these alpha i's to sigma naught. So
Do you need to add all of them, not just one?
that's a good question. You do need to add all of them. And maybe you'll see why in a minute. So what we're going to do is,
But couldn't there be infinite ones that are false under that case?
but we only need one. So sorry, yes, we only take one for a particular I, but then we repeat this for all I.
Exactly.
Yeah, so we have at most 2 to the n of these different situations. For each one, we pick an alpha I, and we add that one to our set. Thank you. So we define this to be alpha I for all I, yeah, let's just say for all I. And we know that this set is going to have at most 2 to the n entries. Yep.
Just to be clear, the truth assignment where you said would be alpha I, is that vi still? That's still the
Yes, thank you. That's the ith truth assignment. Okay. So we define sigma naught as such, and then our claim is that sigma naught satisfies our requirements, that sigma naught will logically prove alpha. So let's see why this is the case. So our claim is that sigma naught logically implies alpha, but that's also equivalent to sigma naught combined with not alpha being not satisfiable. So it suffices to show that due to our fact. Okay? So to show that this is not satisfiable, what we'll do is assume by way of contradiction that it is, and then see what happens. So assume by way of contradiction that sigma naught combined with naught alpha is satisfiable. Well, what does it mean for that to be satisfiable? Well, we use our definition. That means that there exists some truth assignment V that satisfies that. So if it satisfies that, then V of naught alpha is true, which means that V of alpha is false. So that means that under this truth assignment, we're in one of the rows in our truth table that we picked where alpha was false. But what do we know about our construction of sigma naught? Well, we know for each of those rows, we made sure to pick at least one alpha I that isn't true under this assignment. So stated more formally, what we are basically saying is that since V satisfies that, it also satisfies sigma naught, which means that that's going to be true for all I. But we specifically chose our alpha i's to be false under these rows in the truth table. So that's a contradiction. Okay? So this proves the theorem of finite models. But now you might ask, why is this particularly interesting? Well, it ends up having some deeper connections to some other important theorems. So, yeah, I guess before I go on, I just want to make sure that the high-level intuition of this proof kind of makes sense. So the whole idea of what we did here basically is that even though sigma and alpha are taken from, sigma is an infinite set and alpha is taken from infinitely many propositional variables, the truth table itself only has a finite number of false entries. And for each false entry, we basically only need one representative to cover that part of alpha. Okay, so before I introduce the next theorem, what I'll do is, for sake of brevity, we'll have a definition, and then we'll just refer to that definition by a shortcut to make things a bit cleaner. So what we're going to do is define the notion of finite satisfiability. So we'll say sigma is finitely satisfiable. And we'll just use the shortcut of saying fs to make our lives easy. Sigma is finitely satisfiable if and only if every finite subset of sigma is also satisfiable. So for all sigma naught that are subsets of sigma, and sigma naught is finite, then sigma naught is also satisfiable. So that's just our definition of what it means to be finitely satisfiable. And the interesting theorem is that no matter what sigma you give me, sigma is satisfiable if and only if it's finitely satisfiable. And this is commonly referred to as the compactness theorem. This is one of the famous theorems that Kurt Gödel proved way back in the 1930s. And we're going to prove it here today. So why is this theorem important? Well, it ends up being connected to the theorem of finite models. And to see why, what we can actually do is make the following statement. The finite models theorem, so that statement is true if and only if the compactness theorem is true. So if you know that theorem is true, which we proved, then using that you can prove the compactness theorem. And the converse is also true. If you hadn't proven finite models and you had proven compactness theorem, you could show that that implies finite models. So these two theorems are essentially saying the same thing. And so we can get an idea of why this is true by showing one of the directions. So this direction ends up being pretty easy. So we're going to assume that compactness is true and then use it to show that finite models is true. So in order to show that finite models is true, we have to show that this statement holds for any sigma and any alpha. In order to do that, we're going to prove it by contrapositive. So by contrapositive, what is the contrapositive of the finite model theorem? Well, we have to basically suppose the negation of the conclusion. So we have to suppose that for every finite subset of sigma, you do not logically imply alpha. So let's suppose for all sigma naught, where sigma naught is finite, that sigma naught does not imply alpha. So that's what we know. Now, what we can do is use that fact over there again. And from that, we know that sigma naught together with naught alpha is satisfiable. Okay? And sigma naught combined with naught alpha is satisfiable for all such sigma naughts that are subsets of sigma and are finite. But if this is satisfiable for all finite subsets of sigma, that's precisely what it means to be finitely satisfiable, right? It's precisely that definition. So by the compactness theorem, we know that sigma combined with naught alpha is also satisfiable. Okay? Yep.
How how does the union carry through the compactness theorem like that?
So what we essentially did is relabeled that as our sigma. So we're just saying, okay, hold on. So I think I see your question. Okay, so let's think about this for a second. So we know that that's satisfiable for all subsets sigma naught of sigma, where sigma naught is finite.
But see,
If we-
sigma naught union naught alpha is not necessarily a subset of sigma, so you can't directly apply the compactness theorem.
Yeah, I see what you're saying. So it's still true. I'm just trying to think about why it's true. So
Well, is it
So-
sigma not union not alpha a subset of sigma union not alpha?
yeah, that's what I'm thinking. So I think what you do is basically apply compactness to sigma union not alpha.
But then that's not all subsets, since all subsets would include subsets that didn't include the not alpha element.
But even though this, so since this is satisfiable, any finite subset of it is also going to be satisfiable. So you can just drop the not alpha. Well, you don't even need compactness again. You know that this is finite, so any subset of it that doesn't include not alpha is also going to be satisfiable. But yes, thank you for bringing that up, because that is an important detail that I did omit here. So compactness with the note that we're applying it to this and using the observation that if a finite subset is satisfiable, then so is any subset of that finite subset. Okay, does that seem okay now? I think that fixes it. Okay, so we know that that's now satisfiable. And then again, we use our fact to say that we can't prove alpha. And we're trying to show the contrapositive here. So we've shown the negation of what we need to show, so we're good. Okay? So that's how you prove that assuming compactness is true, then you get finite models. But this direction is a lot harder. So, exercise, yeah. But rather than leave you guys hanging in the dark, what we'll do is, so we haven't really proven compactness yet, right? We've proven finite models, and that compactness gives you finite models, but we haven't proven that finite models gives you compactness, because we're leaving that as an exercise. But instead of doing that, what we'll do is just prove compactness directly. And it's a fairly long proof, but what it'll do is actually reveal a few common tricks and techniques that you'll see as kind of a recurring theme in this course, and also get you more familiar with these sort of more difficult proofs. So this is probably one of the more difficult proofs in the course, so it's going to be a little hard to get the first time around. Hopefully what I'll do is post the notes online, so that if there's anything weird or maybe difficult to get at the first time around. Hopefully you can refer back to those. But with that said, we'll get started and see how far we go. So for the proof, what I'll do is basically sketch an outline. So how are we going to prove compactness? So as was the case for the finite models, the finite case isn't really interesting. It's only the infinite case that's interesting for compactness. Also, one of the directions for compactness is also not really interesting. So if we look at the direction that sigma is satisfiable, then it should be clear that any subset of sigma is also going to be satisfiable, right? Because we just take the same truth assignment and it satisfies that same subset. So this direction is trivial. It just falls right out of the definition. For the other direction, the finite case is also trivial, because if we have every finite subset of sigma being finitely satisfiable, then sigma, again, is a subset of itself that's finite, so sigma is satisfiable. Right? It's the exact same logic for, as we said, for the finite model case, where only the infinite case is really interesting because any finite set is a subset of itself that's also finite. Okay? So we're only really interested in the case where we're showing that every finite subset of some infinite sigma is finite, and then using that to show that sigma must be satisfiable. So we're going to do this in multiple steps. The first step is to basically extend sigma to some alpha, or to some delta that's going to be a superset of sigma. And delta is going to have the important property where delta is also finitely satisfiable, and for every well-formed formula, either the formula is in delta or its negation is in delta. So you can think of this, yes?
How do you prove delta exists? Because you didn't say that
Yeah.
sigma itself is finitely.
Yeah, so this is just a proof outline. So I'm just kind of putting out the roadmap of where we're going to go. That in itself is going to be like a couple page proof. Yeah. So once we've done that extension, then what you observe is that, so what we're going to do is find a truth assignment V that satisfies delta. And then once you have such a V, if it satisfies delta, then it must also satisfy sigma. Okay, so that's kind of what we're gonna do. So it's kind of a pretty much just a two-step proof. This is the bigger step, and this is the more tedious step.
But how do you go from V B satisfies sigma, which we already knew from the fact that sigma is satisfiable, or that we have some truth assignment that satisfies sigma, how do you go from that to all finite subsets in sigma?
So we're doing the other direction. So
Oh, okay.
this is
Right.
showing that all finite subsets being satisfiable implies that sigma is satisfiable. Because the other direction
Right.
is
Yeah.
easy. Yeah. Okay. So before we get into the details of this, we'll prove a very useful lemma. And what the lemma says is that there exists some ordering of all well-formed formulas such that every well-formed formula has a unique index. And if any of you are familiar with notions of like countability from taking pure math courses or anything, this might remind you of that. If not, that's okay. You'll probably run into it later on throughout your undergrad. What this is saying is actually kind of deep because it shouldn't be obvious that this is the case. Well, it's intuitive, but it's kind of tricky to show. So if you think about how we're going to try to show this, one strategy you might want to try is, one thing we might try to do is just sort all the well-formed formulas. But there's going to be some problems here because even if you're only looking at the well-formed formulas that are length 1, even you're just looking at the propositional variables, there's infinitely many of them. So even for the case where you just fix the length to some finite value, there are infinitely many indices. That you need to come up with. Yes?
Can we even say that the number of well-formed formulas of length 1 is countable itself?
Yeah, so that's a good question. Yeah, so if you're not familiar with notions of countability, that's okay. We'll come into it later on in the course, but yeah, to answer your question, you can say it's countable, and it basically, in order to say it's countable, you have to assume that the set of propositions is countable. So these theorems have also been proven in the uncountable case, but it takes a lot more work, and there's not really any point to doing that for the purposes of this course. So we're just going to focus on the case where the set of propositions is countable. So the solution is first to come up with a function f that maps the set of possible symbols together with the set of propositional symbols to some natural number. And what we're basically going to do is say there is such an F, say by sorting A. So this kind of implicitly assumes that A is countable. So we're just going to say that there's some sort of mapping that takes us from the set of possible symbols that we can encounter in our propositional formulas and puts them to a natural number. And now we have some alpha, and alpha is finite, so it's a finite sequence of characters. So there are n characters, each from this set of connectives and possible propositional variables. Now what we have to do is come up with a number for alpha. And the solution is actually quite ingenious. So this was probably, I think, the main insight that allowed Kurt Gödel to prove the theorem. You'll sometimes hear it referred to as Gödel numbering. I think there's a Wikipedia page on that. So I'll just write that here. So this kind of insight was important enough to have himself named after it. And the idea is that the number for alpha is going to be P1, fx1. So it's going to be this product where pi is the ith prime number. So we take the first n prime numbers, where n is the length of the alpha that we're trying to encode, and we raise each of those primes to the power corresponding to the number that we got for that individual letter. And the reason this is so clever is because the fundamental theorem of arithmetic says that any natural number is decomposable into a unique set of prime factors. Right? So, fundamental theorem of arithmetic implies that you give me any number, and from that number, I decompose it into its set of prime factors, and that gives me my back my values for f. In particular, it's the number of occurrences of each one of those primes. So this is the number of times the first prime occurs, this is the number of times the nth prime occurs. So what this is saying is that this encoding process that we came up with is in fact reversible. Not only can we take any alpha and encode it into a natural number, but given that natural number, we can go back and say what alpha was. So what that implies is we've come up with a bijection, right? We've come up with a unique integer that identifies alpha. So the number is a unique identifier for alpha. And that's really all we need to do, right? So there's one kind of small little hole that we need to cover up here, which is that some of these numbers that we've came up with correspond to formulas that maybe aren't well formed. Like some of the numbers might give us like, I don't know, right? We might get stuff like that corresponding to different integers. But what we can do is we can just remove all of those integers from our numbering system and just collapse everything down to fill in the holes. The important part is that we're actually able to come up with an identifier that corresponds uniquely to each one of these formulas. So is everyone fine with that? So what we've done is we've rewritten alpha as a sequence of symbols. So alpha is finite, and it consists of n different symbols. And then each of these symbols are mapped through f to give us our different exponents. So basically, the number of times each prime occurs tells you what symbol appeared in that location. Yep.
You have to be a bit careful with mapping the single symbols.
So you mean like with this step?
Yeah, like the signal not or and.
Yeah, so that's included in the domain of things that f can map. So basically, like this would go to 0, this would go to 1, 2, 3, 4, 5, and then you just list out all of the things that are in A. Those, right? And you would do that by just like sorting the stuff in A by some chosen way. All it really relies on is the fact that A is countably infinite, so that you can basically come up with some enumeration over the elements of A. So this insight is important because it basically allows us to establish connections between the set of all well-formed formulas and the set of all natural numbers. And that'll come into play again later on in the course when you try to prove stuff about what the limits are of these logical systems. So that's the first lemma. The second lemma is going to be very different and more taking us back to what it means to be finitely satisfiable. So the second lemma is going to say that if we have some finitely satisfiable sigma, then, and you take some alpha, then it can't be the case that so basically only one of these two options are going to be finitely satisfiable. So first off, it should be clear that you can't have both being finitely satisfiable. So why is that the case? Well, if both were finitely satisfiable, wait, can you have both finitely satisfiable? No, right? Yeah, was it the case that you can't have both finitely satisfiable?
It's easy to show by compactness, but we can't use compactness.
Right.
Because it's all finite sets and, or subsets, and when they contain either, like alpha, not alpha, or
Yeah.
opposite, so it's all finite sets, subsets. Right?
Yeah, so if both were finitely satisfiable, yeah, that's not going to work. But the difficult part is going to be showing that okay, let's just proceed with the lemma. What what we're basically going to do is just assume, by way of contradiction, that this is not the case. So yeah, assume by way of contradiction that both are not satisfiable. So okay. Yeah, so this is really the only case that we need to worry about, because you can't have both being finitely satisfiable. We just need to show that you can't have both of them not being finitely satisfiable. So if we assume that both of them are not finitely satisfiable, then what does that mean? Well, it means each one of them has a finite subset that's not satisfiable. So let's write down what those subsets are. And that means we have some sigma naught. It's a finite subset of that. And we have a sigma 1. It's a finite subset of that. And both of these are not satisfiable. Now, the intuition is we're going to define this sigma prime. That's the union of these two sets without alpha or not alpha. So we've taken our two sets that aren't satisfiable, combined them together, and removed the parts that aren't in sigma. And what do we know about this set? Yeah, first of all, it's a subset of sigma. And second of all, it's finite. Now, we need to show yeah. So what does this tell us, right? We have some finite subset of sigma, and it's finite. So we know that since sigma is finitely satisfiable, that sigma prime must be satisfiable. Right? That just comes from our assumption of sigma. But if sigma prime must be satisfiable, then let's reason about the truth assignment that satisfies it. So if it's satisfiable, then that means there exists some v that satisfies sigma prime. Now, what does such a v tell us? Well, we know that for any alpha, in particular the alpha that we're interested in, either v of alpha is going to be true or its negation is going to be true. Right? You can't possibly have both them be false or, yeah. But then if v of alpha is true, then this must be satisfiable because V satisfies sigma prime, which is a superset of sigma, and V satisfies alpha. So it must satisfy sigma naught. And similarly, if V of not alpha is true, then it must satisfy sigma 1. Again, because V satisfies sigma prime, which is a superset of sigma, and it also satisfies not alpha. So in either case, it satisfies sigma naught or sigma 1. But that's a contradiction because we said that it wasn't satisfiable. Okay. So we've proven our two lemmas. And yes?
I'm sorry, why did you say that two of them can't be both satisfiable?
Where? How did we say that?
We didn't prove that second part. The second part, we said it was trivial. The part of them being both, we didn't show that it's not possible for both of them to be.
Right. Yeah. So is it trivial or?
I don't think it is trivial.
I may have just assumed it was trivial and then not really thought about it. Yeah, that's the problem. We can't just use compactness. So why can't they both be? Okay, here's the thing. Actually, I don't think it matters. That's. I think that's.
They can both be, because what if you had like sigma is just P0 and P1 and alpha is P2? They're both satisfiable.
Yeah, good point. Yeah, so that's okay. So yeah, the bad news is yes, you can have both of them, but the good news is it doesn't matter because we don't need the fact that you can't get both of them. We only need the fact that you can get one or the other, right? We don't care if you can get both. The important part is that you can't have neither, okay? And we'll see that in a second because what we're going to do now is construct our delta, that's an extension of sigma, using these two lemmas. So we're going to construct delta, and lemma 2 is basically going to give us the inductive procedure for constructing delta. We'll do it by, we're going to make an infinite number of different deltas, and then when we're done, we're going to combine them together into our mega delta. So the first delta is just going to be sigma, because we're extending sigma, we're growing it up to basically include all alphas or their negation. So delta naught is just going to be sigma, and then for every I, we're going to make delta I plus 1 equal to delta I together with alpha if this is finitely satisfiable, or together with the negation otherwise. So lemma 2 tells us that this is a well-defined procedure because we're always going to, we can actually be even stronger about what we're saying. So, right. So I'm saying either that's going to be finitely satisfiable.
They both could both be true.
So
You can say
Okay.
if the first one isn't
Yeah.
finitely satisfiable.
You're right. I do have to be a little careful about what I say. So I have to say else, but in the else case, then we know that this is finitely satisfiable. Right? So this is a well-defined construction because we know that we're always going to get at least one of these two cases.
In this case, what are we saying alpha is?
Right, yes. Alpha I, and by lemma 1, we have some ordering for all of our alphas, right? So every I, there's some well-formed formula, alpha I. So we're looping through all of our well-formed formulas, and we're building up our delta larger and larger to encapsulate all of the alphas or their negations. And lemma 2 makes this a well-defined procedure. Now what we're going to do is take delta simply to be the infinite union of all of these delta i's.
Is that necessary since all delta I are already you defined them to include the union in the previous one? So the
yeah.
union of all of them is equivalent to the, I guess union at index infinity. So
Yeah, the important,
it's
yeah.
the union of all of them is equivalent to delta infinity if you could do that, but you can't.
Right, exactly. This is just the limit as I goes to infinity of delta I. The reason I'm preferring this notation over that notation is because this is something we've seen beforehand, whereas this we haven't seen, but they're equivalent. Just because of the fact that each delta I is a superset of the previous one. But now we can make a number of statements about delta. So we know a number of things about it. So what do we know about delta? So first of all, sigma is a subset of delta. That's easy. Second of all, we know that for every well-formed formula alpha, either alpha is in delta or not alpha is in delta. Those two things are pretty easy to see. The last part that's a bit tricky is that delta is finitely satisfiable. So why is it the case that delta is finitely satisfiable? Well, we know that every delta I is finitely satisfiable, right? But that doesn't necessarily imply that delta is finitely satisfiable because we're taking the limit off to infinity. But you can observe that any finite subset of delta is also going to be a finite subset of some delta I, right? We can always find the biggest I that includes the finite subset that we're considering, and then we know that that delta I is finitely satisfiable. So stated more clearly, every finite subset of delta is also a finite subset of some delta I. Right? Because it's finite, so we can just look at everything that it includes and then pick the smallest I that encompasses it. So that tells us that delta is finitely satisfiable. And now, knowing all of these things, we are now ready to proceed to the next step. So I think in the proof outline, this is now a check mark off the first step, where we've now successfully extended sigma to this kind of like maximal set. And what we need to do is show that delta is satisfiable. Because if we can show that delta is satisfiable, then we've shown that sigma is satisfiable, and that's what we need to do, right? We're trying to show that if all the subsets are finitely satisfiable, then sigma is satisfiable. So the reason we've done this extension is because it allows us to define a truth assignment that will satisfy delta. So what we'll do is use our construction to prove that the following truth assignment actually works. So define V to be the truth assignment such that it returns true if P is in delta, and false if P is not in delta. And that's for all P in our core set. And this is well defined because either P is in there or P isn't. And we just have to define the truth assignment for all of our core propositional variables. And then once we have that, we can extend it to the set of well-formed formulas using the definition we've seen before. And what is left to show is that our delta is satisfied by this truth assignment. And in fact, we'll actually show a much stronger claim that it's only the only things that are, so the claim is that the only things that are true under this truth assignment are the things in delta. So this truth assignment kind of tells you everything about delta in a sense. And such a truth assignment satisfies delta, right? Because everything that's in there is also satisfied. The reason we're showing something strictly stronger than we actually need to show is because we kind of need both directions in the inductive step. So the proof will be by structural induction on all well-formed formulas. Let's see if I can rush through this. Might not be possible. So the base case we know that alpha is in our core set, but then V of alpha is true if and only if alpha is in delta. And that's just by our definition, or by our choice of V. Now, the inductive step is where things start to get a bit tricky. Now, what we're going to do to simplify our lives is use the fact that we know not combined with the and are adequate. So since we know they're adequate, any other cases can be expressed as some combination of not and and. So we only have to show the cases where alpha is made up with those two connectives. So we'll show this case first because it's easier. So we're going to suppose that alpha is not B. Now, we need to show that the truth value of alpha is true if and only if alpha is in delta. So what do? We just look at the truth value of alpha. Well, the truth value of alpha is going to be it's going to be true if and only if the truth value of beta is false by the truth table, right? But this is going to occur if and only if beta is not in delta by our induction hypothesis. And you can see this is why we actually needed both directions. So this is why we needed the if and only if in our claim. But if beta is not in delta, then we know that not beta is in delta by the construction of delta.
Wait, doesn't that, wait, no.
But if not beta is in delta, well, not beta is alpha, so it's in delta. So we're good. Right, that's what we needed to show, that the truth value of alpha is true if and only if it's in delta. Now, we don't have time for the second case, but what we're basically going to have to show is that when you have beta and gamma, that this thing is true if and only if alpha is in delta, and it's going to be a more complicated version of what happened here. So you basically just show that V alpha is true if and only if V beta is true and V gamma is true. Right, that's by the truth table. But this occurs if and only if beta is in delta and gamma is in delta by our induction hypothesis. And for the remaining part, you basically have to show that if this is true, then you get alpha ending up in gamma or ending up in delta. And if you suppose this is false, then you end up having alpha not in delta. And it ends up being a bit trickier than that because you can't just use the fact that not beta equals alpha because you don't get the not symbol appearing in the delta construction. So the rest is an exercise, maybe? Or maybe it'll be posted later, or Shai will complete this next lecture. But that's it for now. Thank you.